In this problem, we focus on the location routing problem, often called LRP. It integrates two decisions that are usually separated: where to open depots and how to route vehicles to serve customers. The goal is to minimize total system cost. That cost includes the fixed cost of opening facilities and the variable cost of transportation along the routes. The location routing problem matters because it connects strategy and daily operations. Facility location decisions shape the entire distribution network, and routing decisions determine how the network performs in practice. Because it combines facility location and vehicle routing, it inherits the difficulty of both. That is why solving the decisions separately can easily create an expensive overall system. The scenario is a national retail company expanding into a new region. The company has multiple candidate sites for distribution centers, each with a fixed construction and operating cost. Retail stores have known demands, and the company uses delivery trucks with limited capacity. The location routing problem asks you to choose the depot sites and the routes in one integrated plan. This slide highlights the core trade-off. If you open more depots, you often reduce driving distance and can create shorter routes. But every opened depot adds a fixed cost. If you open too few depots, you may save on fixed costs but pay a lot more in transportation, and you may need additional vehicles because of capacity limits. This chapter uses a tiered toolkit. Tier 1 gives a mixed integer programming model that describes the problem precisely. Tier 2 uses a classic heuristic called greedy randomized adaptive search procedure. Tier 3 uses a nature-inspired meta-heuristic called the gray wolf optimizer. Tier 4 uses transformers, a deep learning architecture as an augmentation method. Then tiers 5 through 9 extend the decision-making system using simulation, autonomy, ethics, and quantum optimization. Tier 1 is the pen and paper baseline. The model includes decisions for opening depots, assigning customers to depots, and routing vehicles. The objective is to minimize the total cost, meaning fixed depot opening cost plus travel cost along all routes. Constraints ensure assignments are valid, vehicle routes conserve flow, vehicles respect capacity, and assignments only go to depots that are opened. This slide defines the sets used in the model. We have a set of customers and a set of candidate depot locations. We also define the set of all nodes, which includes both customers and depots. Finally, we have a set of vehicles. These sets provide the indexing structure for assignments and routing decisions. Here we list the key parameters. Each candidate depot has a fixed opening cost. Each customer has a demand value. Every vehicle has a capacity, and travel between any pair of nodes has a cost or distance value. Together, these parameters define the cost trade-off and the feasibility limits. This slide defines the decision variables. The first variable indicates whether a depot is opened. The second indicates which depot each customer is assigned to. The routing variable indicates whether a vehicle travels directly from one node to another. These variables connect strategic facility decisions with operational routing decisions. The objective function minimizes total system cost. The first term sums fixed cost for every depot that is opened. The second term sums routing travel costs across all arcs and vehicles. This structure captures the fact that you pay once to open a facility, but you pay continuously for transportation over time. These constraints ensure correct customer assignment. Every customer must be assigned to exactly one depot. The activation constraints link assignment to opening. Customers can only be assigned to depots that are open. A big constant is used so that if a depot is closed, assignments to it are forced to zero. These constraints capture vehicle routing feasibility. Flow conservation ensures that for each vehicle, what enters a node must also leave it, so you do not create disconnected paths. The vehicle capacity constraint ensures that total served demand on a vehicle route does not exceed capacity. This is one of the main reasons integrated planning matters. Capacity limits can force you to use multiple routes. In the concrete example, there are 2 candidate depots and 3 customers. Depot 1 has fixed cost 100, and Depot 2 has fixed cost 120. Customer demands are 10, 15, and 20, and vehicle capacity is 30. Since total demand is 45, one vehicle is not enough, and you need at least 2 vehicles. A plausible solution opens Depot 1 and creates 2 routes. One route serves customers 1 and 2, and another route serves customer 3. This figure visualizes the decision space. You choose which depots to open, and then you design routes from the opened depots to visit customers. The key idea is that depot decisions and routes cannot be separated safely. A depot that looks attractive on fixed cost may lead to long routes, while a depot that is more expensive may create much lower transportation cost. Tier 2 uses greedy randomized adaptive search procedure. The algorithm alternates between building a feasible solution and then improving it. Randomization is controlled through a restricted candidate list. Instead of always choosing the single best greedy move, the method chooses randomly among top candidates, which helps explore diverse solutions. In the construction phase, you start with an initial depot opening and empty routes. You compute insertion costs for adding each unassigned customer to routes. Then you build a restricted candidate list containing the best insertion options, and you select one option at random from that list. Repeating this step builds a complete feasible solution. In the local search phase, you take the constructed solution and try to reduce its cost with neighborhood moves. Typical moves include swapping customers between routes, moving a customer to a different route, or performing route improvements such as 2-opt. You continue until no move yields improvement. In this part, you can see the implementation details in action. Key functions in this chunk include get construction candidates and construct solution. You will notice logic related to route. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. Key functions in this chunk include local search and grasp for LRP. You will notice logic related to iteration. As you read it, focus on the sequence of steps and which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. Tier 3 introduces the gray wolf optimizer. It is a nature-inspired method that uses a social hierarchy to guide the search. The best 3 solutions act as leaders, and the remaining solutions update their positions by moving toward these leaders with controlled randomness. For location routing, this requires an encoding and decoding step so that the search can work with discrete decisions. This figure illustrates the idea of the gray wolf optimizer. Leaders guide the rest of the pack toward the best solution, which you can think of as the prey. In optimization terms, the prey is the lowest cost solution. The visual emphasizes leadership, guidance, and convergence over time. To apply the gray wolf optimizer to location routing, we need a representation of a complete solution. A wolf position encodes depot openings, customer assignments, and route priorities. Fitness is the total cost, depot fixed costs plus route travel costs. After each update, the continuous position vector is decoded back into a feasible, discrete solution so it can be evaluated. Tier 4 uses transformers, which are deep learning models built around self-attention. For routing, self-attention can learn which customers are related, such as being close geographically or having compatible demand patterns. A model can generate a route step by step, selecting the next customer to visit. With additional structure, the model can also suggest which depots to open. This figure highlights what self-attention means operationally. The model learns a dense relationship map across customers. A high attention weight between 2 customers suggests they are good to visit consecutively in a route, often because that sequence reduces travel cost or improves feasibility. Tier 5 embeds location routing inside a digital twin. Instead of solving one static instance, you simulate the network with depots, vehicles, customers, traffic, and disruptions. This allows what-if scenarios such as fuel cost increases, demand shifts, or depot closures. The system can then trigger re-optimization when key assumptions change. Tier 6 replaces a single centralized solver with multiple autonomous agents. Customer agents broadcast demand and service requirements. Depot agents bid to serve customers based on expected costs, and vehicle agents negotiate route construction. The location routing solution emerges from these decentralized interactions, which can scale and adapt more easily. Tier 7 focuses on collaboration. The system proposes a small portfolio of diverse, high-quality solutions, not just one. Explainability is essential so humans can understand trade-offs, such as cost versus resilience. Humans can add strategic knowledge like avoiding a floodplain location, and the system then recomputes solutions quickly. Tier 8 expands the definition of optimal. The model can incorporate fairness, sustainability, and labor welfare. That means you may add constraints to ensure equitable service across neighborhoods, include carbon emissions as a penalty or cap, and prevent excessively long routes that create safety risks for drivers. Tier 9 introduces a quantum-inspired direction for very large problems. Quantum approximate optimization is a hybrid approach that combines quantum circuits with classical parameter tuning. The first key step is translating the location routing problem into a quadratic, unconstrained binary optimization form so that it can be represented as an energy function for a quantum system. This slide shows the quadratic, unconstrained binary optimization form. It is a way to represent costs and constraint penalties using only binary decisions. In practice, the coefficients are derived from depot opening costs, routing costs, and penalty terms that enforce feasibility. The goal is to find a binary assignment that produces the lowest energy, which corresponds to a low-cost logistics plan. This figure shows the hybrid loop. A classical optimizer proposes parameters for a quantum circuit. The quantum system is executed and measured to estimate solution quality, and the classical optimizer then updates parameters to search for lower energy states. Over iterations, the process aims to find a high-quality approximate solution. These practice questions help you test understanding across tiers. Start with Tier 1 by computing total cost for a given depot and route plan. Then work through heuristic and meta-heuristic thinking by forming restricted candidate lists and proposing an encoding for the gray wolf optimizer. Finally, connect modern methods by interpreting attention matrices, digital twin scenarios, and the meaning of a ground state solution in quantum formulations. The main lesson is that location decisions and routing decisions are tightly linked. You need an integrated approach to balance fixed facility costs and transportation cost. A rigorous Tier 1 model provides clarity while heuristics, meta-heuristics, and learning methods help scale. Digital twins and ethics broaden decision quality, and quantum approaches offer a future path for extremely large instances.